right, everybody ready to go? Back from break. All right, we had left off, getting ready to start a standard deviation. So we had started our table by finding the difference between the value and the mean. So we want to continue with that. The next part of our table is to square this value, this difference that we had found. So we want to square -25. So that's going to give us 625. We want to square 25 again. That gives us 625. We want to square 15, which gives us 225. I know that zooming in and out probably gives you a headache. We want to square -5, which gives us 25. We want to square 5, which gives us 25. We want to square -15, which gives us 225. And that is the only reason that square is in that problem, is to make all those negatives become positive so that we no longer get 0. Every time you do this difference, you'll always get 0 for that sum. And that's kind of like a check that you can do. If you don't get 0 when you do that difference, you've done something incorrect when you've done your differences. You should always get 0 when you do that difference in that column. So that should always happen there. And then the reason we have the square in the formula is to make those negatives disappear, and we get great big numbers, yes, but that is to get rid of the negative values as we do our calculations. So that is the purpose of the square sign in the formula. So then you've got your sigma symbol, and so that means add up that column. So that is the next step, is to add up that column. So let's add up that column. What is the total in that column? So everybody add that column up. Just be sure that we all get the same answer.
I got 1750.
That is right. Everybody get that? When you add that column up, everyone should have gotten 1750. So we're ready to go over here and put it into our variance formula for the population. So if we put this into the formula, everything that's in that numerator is right there in that number, 1750. We have done everything that's in that formula. There's that number, 1750. So it may look all tough and complicated, but by breaking it down and putting it into the formula, there it is. That's all you have to do to get that answer. So using the table to help you get there, it kind of makes it simple for you so that you know how to get there. Is that helpful? Even though that formula looks all crazy, by breaking this down, it's not so bad. Now, what's that N mean? The N means how many of these numbers in the data do you have? How many are there? There's 6 of them. So that's all there is to that formula. So what's our next step? We're going to take 1750 and divide it by 6. What do we get? The variance is 1750 divided by 6, or 291.7. That is the variance. Now, if you know the variance, can you find the square root? Yes. All you have to do is take the square root of that to find the standard deviation. So what is the standard deviation? You should be getting 17.1. Now this part of statistics is where the calculator is vital. You are going to need a calculator to do this part of statistics. A lot of things that we have done has not been very math intensive, but this part of statistics is going to be vital that you have access to a calculator. Any questions? I hope I've tried to make that pretty simple for you. Now, I've already seen that I've made a mistake. If you will go back to your notes, there is a mistake in a formula, and that is on the sample formula. The variance should be n-1, and the standard deviation should be n-1 there. So please be sure you go back and make that change. Everybody got that? Okay, now let's do the same calculation. So all of these were with population. Notice the symbols that I used. Population. So if I wanted to do the same calculation, but to do it with sample, this part of the table is really the same. That doesn't make any difference. Whether I had mu here or the X with the bar, that part of the table is the same. So if I go here to do the sample, it's going to still be the same except for this number. So that's 1750 is still the same. We're going to have S squared instead of the Greek letter. Instead of 6, we're going to have 6 minus 1, which is going to be what? 5. So we're doing 1750 divided by 5 this time. What does that give you? What is 1750 divided by 5?
350.
350. So the variance is 350 with the sample. And then how are you going to find the standard deviation? You're going to take the square root of 350, which is going to give you 18.7. So they are very close in answers, but not exactly the same. Very close in answers, but not exactly the same. One is population, one is sample. That's the only difference in those two answers. Now, another measurement of variation something called the coefficient of variation. Some textbooks talk about this, some textbooks do not. There's not an official symbol for it, but we're going to take the standard deviation, divide it by the mean, and multiply it by 100 in order to get a percent for the answer. And the reason you would use this particular measurement is that you have two different data sets and you want to compare those standard deviations, and the units are different. So let's look at an example of when this might be helpful. We sell cars over 3 months. The mean is 87 and the standard deviation is 5. The commission on the sales over the same time period has a mean of $5,225 and a standard deviation of $775. Now, is there any way to compare the mean of those two values or the standard deviation of those two data sets? No. One's numbers, one's in money. So there's not going to make sense of the two together. So we're going to find the coefficient of variation for each of them. So for the number of cars, we're going to do the standard deviation, which is 5, over the mean, which is 87, times 100. That's going to give us 5.57%. For the commission, we're going to get the standard deviation 775 over the mean 5,225 times 100, which is going to give us 14.79%. Now these two percents can be compared. Which is giving the bigger result? Commission or the number of cars being sold? So we can say that the commission is almost 3 times more than the sales based on that comparison. Okay, some of what we're going over is terminology. Some of it is going to have to, you're going to have to work through a problem or so on your own for it to kind of make sense. When you look through the PowerPoint that will be posted later today that kind of summarizes what we've gone over, there will be some instructions on those of you who have a graphing calculator, how to use some functions with the graphing calculator to do this with a calculator. So that is one advantage to having the graphing calculator. There are some features there that does this automatically. If you don't have a graphing calculator, maybe you have a friend who has one that you can borrow for the time being. It is a good advantage for doing standard deviation, so that kind of makes that calculation a little bit easier. You can use it to check. So that is an advantage for having the graphing calculator. I don't want you to go out and purchase one just for this one type of problem. They're kind of expensive, so I wouldn't want you to do that. But if you do know someone who has one that you could borrow, I would suggest perhaps doing that. So that information will be either in a video or in the PowerPoint that I will post later today. So that information will be there. We just don't have time to really go through the ins and outs of doing that right now in this session. But I will get that information posted for you. Any questions so far? All right, next item on the agenda is another measurement of position. And it's called a Z-score. A Z-score is often used because it also, like the coefficient of variation, can be used when the units are different and we want to compare two different data sets and the units are different, so we want to talk about how they are alike or how they are different, and we can use the Z-scores to help compare those measurements together. So the Z-score is considered to be a standard score, and actually Z-scores are used more often than you will see the coefficient of variation. The way that you calculate a Z-score is you're going to take the data value minus the mean, divide it by your standard deviation. So this is the way that you calculate a Z-score. Now, to understand a Z-score a little bit, you need to think of a Z-score on a number line. And at 0 is your mean. If you have a Z-score of 0, you are at the mean or the middle of your data. So if your Z-score is positive, that means you are above the mean. If your Z-score is negative, then you are below the mean. So that's what you need to know about Z-scores. So Z-scores that are positive, you are above the mean. Z-scores that are negative are below the mean. So that's the first thing that you need to know about interpreting Z-scores. So a Z-score of 0 means you're right at the mean. Z-scores that are positive means you are above the mean. A Z-score that's negative means you are below the mean. So a Z-score of 1.5 means you are above the mean. A z-score of negative 0.8 means you are below the mean. And the z-score values, the units for z-score are in standard deviations. So as we expand this number line, we are 1 deviation above, 2 deviations above, 3 deviations above, or 1 deviation below, 2 deviations below, 3 deviations below. Although you can go more than that, above or below, it is unusual to be more than 3 above and more than 3 below. So you can be more than that, but it is unusual to be more than that. So it is possible, but it is unusual to be more than 3 units above or below in z-score. And then we add to z-score the data distribution. The normal bell curve. So here's our number line at 0. If you have a normal bell curve, where is most of your data going to be grouped at? It's going to be grouped in the center, around the mean. And then very few items are out here on the ends. So that normal data peaks at the mean, bunches in the middle, and then very few at each end. So those outliers are way out here on each end. The mean is there at the peak. So what happens? 50% of the data is on each side of the mean. 50% here, 50% on each side. So then we get into what's called the empirical rule. Someone has studied and studied this data and said, okay, if I look at one standard deviation away, 68% of all data falls within those 2 deviations. Well, if I only look on one side from the mean to one standard deviation, what percentage of data is that? If both of them is 68%, what is from the mean to one of them? What percentage is that? Half of 68 would be how much?
$34.
Yes, 34% from the mean to one standard deviation. So just keep that in mind. Okay, the empirical rule also says that 95% of all data is within 2 standard deviations. So that means we go out a little bit more. And from here to here is 95%. So everything within that grouping is 95%. So if I'm going from the mean to 2 standard deviations, how much is that? How much is it from the mean to 2 standard deviations away? What is half of 95%? That doesn't come out all nice and even, does it? What is half of 95%?
47.5.
Yes, 47.5%. But then you also get into questions of, well, what is it, if this is 34%, what is it from here to here? So that would be 47.5 minus 34. What percent is that? That is only 13.5% just in this little part, from 1 deviation to 2. So you also get into that rule. The last rule is 99.7% of all data is within 3 standard deviations So what percent is from the mean to 3 standard deviations. .85%. Well, what about this little percent out here? If 97.7%, what about that? What's 100 minus 99.7? What does that leave? 0.3, right? But that has to be split on each side. So what do you do with it? You divide it by 2. So that is 0.15 on each end. That's not accounted for. How would you find this little part? Just like we found this part, we did the 34 plus the 47.5, and we would subtract it from the what? Or would we just take 47.5 and subtract it from 49.85? That gives us 2.35 for that little section. But the 3 parts of the empirical rule are this, this, and this. We found the other values because they were implied from the empirical rule. Now let's look at some sample questions. We just have a couple of minutes left, so let me just do a couple of questions. We won't be able to do many. Everybody got this information down about empirical rule? If not, we'll just stop here so you can get that information down. Do we need to stop here so you can finish this information? Or do you want to see a problem yet? Tell me what you need. All right, you're going to see some problems in your homework dealing with z-scores. You're going to see some problems in your homework dealing with the empirical rule. You're going to have some problems with standard deviation. As far as Thursday, we're going to be looking at using, also you're going to get another presentation on some more graphs, but you've used graphs before, so I think you will see that mostly as review. I just don't think we have enough time to do the spreadsheet activity, so I think I'm going to scratch that. The way our timeline looks is we're going to look at Thursday as finishing up with scatter plots and correlation coefficients. We're going to finish up with do a little bit more with Z-scores using a Z-score chart. We're going to look at the review for your test. Your test will be Monday for statistics. Thursday will be our last actual class meeting. Your exam for this class will be Thursday. Tuesday next week is considered a reading day and a study day to get ready for exams. So your exams will be Wednesday and Thursday next week. So Monday, Wednesday, Friday classes, exams will be Wednesday, and then Tuesday, Thursday classes will be on Thursday of next week. So Tuesday of next week is considered a reading study day. So we won't have class on Tuesday. But you'll be taking your statistics test on Monday. I'll have a review for you. I'll get that out over the weekend for the exam. The review for the exam will be comprehensive. It will cover all topics that we've done. The exam mostly will be true, false, and multiple choice questions, but it will cover topics from everything that we've done. Any questions? I think I covered everything that you might want to know, need to know.
Is the exam going to be in person or online?
It will be online, just like your tests have been.
All right, thank you.
Okay. If you need any help between now and test or now and exam, I'll be glad to set up one-on-one meeting times online with you to work through problems, to work through any rough parts, to go over any topics that you want to do. You just need to let me know. We'll work out a time so that we can do that. I'll go over any particular problems or questions that you have. You need to ask for the help. Don't be afraid to do that. Don't be hesitant about that. Anything else you have a question about, unsure about? All right. All right, that's it for today then. Okay. All right. See you.
Bye.
Bye.